What if everything we assume about life in the universe is wrong? We spend so much time imagining aliens as variations of ourselves, carbon-based, breathing oxygen, bound by the same rules of biology that shape life on Earth. But what if the most extraordinary life forms out there aren't built like us at all? Picture a creature whose veins flow not with blood, but with molten rock. A being that thrives in temperatures that would vaporize a human, or in the crushing depths of a gas giant where no carbon molecule could survive. This isn't science fiction, it's a real scientific possibility. Silicon-based life could rewrite the rules of biology as we know it, and today we're diving into the breathtaking implications of this radical idea. Think about it, every living thing on Earth, from the tiniest microbe to the largest whale, shares the same basic chemical blueprint. Carbon is the backbone of our DNA, our proteins, our very existence. But silicon, a close cousin of carbon on the periodic table, could form the foundation of life in ways that defy our wildest imaginations. Imagine organisms with crystalline structures instead of cells, metabolizing sulfur or ammonia instead of oxygen. Envision ecosystems thriving in the scorching heat of volcanic vents or the frozen voids of deep space, where carbon-based life would crumble in seconds. The universe might be teeming with such creatures, so alien to us that we'd struggle to even recognize them as alive. This isn't just speculation, it's a frontier of astrobiology that challenges our deepest assumptions. Scientists are already probing the limits of where life could exist, from the acid clouds of Venus to the subsurface oceans of Europa. And if silicon-based life is possible, it opens doors to entire worlds we've never dared to dream of. What would their civilizations look like? How would they communicate or perceive reality? The answers could redefine our place in the cosmos. So buckle up, we're about to explore one of the most profound questions in science. Are we alone, or is the universe filled with life so strange, so different, that it's been hiding in plain sight all along? Carbon is the ultimate multitasker of the universe, nature's favorite building block for life as we know it. It all comes down to chemistry. Carbon atoms have this incredible ability to form strong, stable bonds with up to 4 other atoms at once, creating endless chains, rings, and complex structures. That's why it's the backbone of every protein in your body, every strand of DNA, every molecule that makes life possible. Picture a molecular Lego master snapping together in countless configurations to build everything from the sugar in your coffee to the neurotransmitters firing in your brain right now. But carbon's brilliance comes with limits. On Earth, we're coddled by gentle temperatures, liquid water, and just the right atmospheric pressure. Take carbon out of this Goldilocks zone and it falters. In the searing heat of a lava flow, carbon-based molecules break apart. In the crushing pressures at the bottom of an ocean trench, they collapse. Even in the frozen vacuum of space, radiation shreds them like tissue paper. That's why scientists get so excited about silicon. It shares carbon's knack for forming multiple bonds, but with a twist. While carbon dances gracefully in our temperate world, silicon thrives where carbon crumbles. Imagine a diamond surviving a blast furnace where coal would vaporize. That's the kind of rugged durability silicon-based life might exploit. Yet here's the catch: silicon isn't as versatile as carbon when it comes to the delicate chemistry of life. On Earth, silicon mostly sits around as rocks and sand, stubbornly refusing to form the intricate, self-replicating structures that carbon does so effortlessly. But what if, under extreme pressures or scalding temperatures, silicon could be coaxed into something more? Deep in the magma chambers of alien worlds or in the hydrocarbon lakes of Titan, silicon might just have the last laugh. While we're bound to our fragile carbon chains, life elsewhere could be built on foundations we've barely begun to imagine. silicon sits right below carbon on the periodic table, a detail that might seem minor, but it's the reason scientists can't dismiss it as a potential foundation for life. Both elements belong to group 14, meaning they share a critical trait, the ability to form 4 chemical bonds at once. This versatility is why carbon builds everything from DNA to enzymes, and in theory, silicon could pull off similar molecular wizardry. Picture carbon as the star quarterback of biochemistry, agile, adaptable, perfect for Earth's game. Now imagine silicon as its burly linebacker cousin, slower but far tougher, suited to harsher playing fields where carbon would falter. The real magic happens in extreme environments. While carbon-based molecules unravel in scorching heat, silicon compounds laugh in the face of fire. Take silica, the main component of sand, which remains solid at temperatures where carbon-based proteins would disintegrate. On a planet where volcanic vents spew 1,000-degree plumes, or in the searing atmospheres of gas giants, silicon stability could make it the ideal scaffold for life. Even its byproducts hint at possibilities. On Earth, carbon life breathes out carbon dioxide, a gas, but silicon might exhale silicon dioxide solid crystals like quartz. Imagine an alien forest where the trees breathe sand instead of air, yet silicon has quirks that carbon doesn't. In water, which is essential for Earth's biochemistry, silicon compounds often clump together into inert rocks. But swap water for liquid methane or sulfuric acid, and suddenly silicon's chemistry gets interesting. On Saturn's moon Titan, where rivers of hydrocarbons flow, silicon might form complex structures impossible in our oceans. And let's not forget duration. Silicon bonds last longer under radiation, a bonus for life on planets without protective atmospheres. The kicker, we've already seen silicon mimic life in labs. Chemists have created self-assembling silica structures that grow, replicate, and respond to their environment, blurring the line between geology and biology. If this can happen in a beaker, what might eons of evolution cook up on a planet with endless time and alien conditions? Silicon life wouldn't just be different, it could rewrite the playbook on what biology even means. At first glance, silicon seems like the perfect backup player to carbon. Same team, similar skills. But when you zoom in on the chemistry, the differences become glaring. Carbon bonds are like precision-engineered handshakes, strong and flexible, holding together even when life's molecular machinery is in constant motion. Silicon bonds, on the other hand, are more like a firm grip that tires quickly. They're bulkier, less nimble, and far more prone to snapping under the dynamic conditions life requires. Here's the catch: while carbon effortlessly forms double and triple bonds, allowing for intricate structures like DNA spirals or enzymes folds, silicon struggles to maintain such complexity. It's like comparing a master origami artist to someone who can barely fold a paper airplane. Then there's the waste problem. When carbon-based life metabolizes, it produces carbon dioxide, a gas that easily floats away. But silicon metabolism would leave behind silicon dioxide, better known as quartz or sand. Picture a silicon-based organism trying to breathe out tiny grains of glass. On Earth, that's a death sentence. Imagine your lungs filling with sand every time you exhaled. Yet on a scorching planet with sulfuric acid atmospheres or methane seas, this quirk might not be a flaw but a feature. In extreme heat, silica could dissolve into liquids like molten sulfur, creating a circulatory system where waste becomes a building material. The real wild card is temperature. Carbon's elegance falls apart when things get too hot. Proteins denature, DNA melts, but silicon's stubbornness becomes an asset in hellish environments. On a world where temperatures hover near 1,000 degrees, silicon bonds might finally have the stability carbon lacks. Deep in the crushing pressures of a super-Earth's mantle, where carbon would crumple, silicon compounds could form durable, lattice-like structures. Think of it as nature's version of reinforced concrete. Even radiation, which shreds carbon-based molecules in space, might barely phase a silicon organism with crystalline armor. Here's the twist: we've already seen hints of silicon's potential in Earth's extremophiles. Bacteria in volcanic vents use silicon to strengthen their cell walls, and some lab experiments show silicon mimicking organic reactions in blistering heat. It's not proof of alien life, but it's a tantalizing clue that our chemistry isn't the only game in town. The universe might be full of life that doesn't play by Earth's rules, organisms that see our ideal conditions as utterly inhospitable. So while carbon reigns supreme on our cozy planet, silicon could be the dark horse of the cosmos, waiting for its moment on a stage we've only begun to imagine. The most inhospitable corners of the universe might be paradise for silicon-based life. Imagine a planet where the ground isn't just hot, it's molten, with rivers of lava stretching for miles under a sky choked with sulfur clouds. On Earth, such a place would be a death trap, but for silicon organisms, this could be the perfect cradle. High temperatures that reduce carbon-based molecules to ash might instead energize silicon chemistry, allowing complex structures to form in the scorching embrace of a perpetual inferno. Volcanoes wouldn't be disasters here, they'd be life-giving vents, spewing not just heat but the raw materials for growth and metabolism. Picture towering silicate formations growing like trees, their branches crystallizing in the blistering air, fueled by the planet's geothermal heartbeat. Then there are the ice giants, worlds like Uranus or Neptune, where pressures are so intense they turn gases into slushy oceans of water, ammonia, and methane. For carbon life, these depths would be a crushing nightmare, but silicon's resilience could turn this into an advantage. In the pitch-black abyss, where temperatures hover near absolute zero yet pressures keep substances strangely fluid, silicon might form exotic, slow-moving life forms. Their metabolisms could run on geological timescales, relying not on sunlight but on the faint warmth of radioactive decay or tidal friction. These beings might resemble living crystals, growing imperceptibly over centuries, their bodies tuned to the rhythm of a world where time itself moves differently. Even planets with surfaces as barren as Mars could hide silicon life beneath their crusts. Mars's rusty soil is rich in silica, and its deep underground aquifers, if they exist, might host microbes that evolved to use silicon in ways we can't yet fathom. In the deep ocean trenches of Europa or Enceladus, where hydrothermal vents melt through icy shells, silicon compounds could dissolve into exotic chemistries, forming delicate glass-like structures that pulse with energy. Life here wouldn't need oxygen or sunlight, just the steady churn of minerals and heat, a recipe written in stone rather than DNA, the most mind-bending possibility. Rogue planets adrift in interstellar space with no star to warm them. On these frozen nomads, silicon life might exist in a state of near-suspended animation, awakening only when geological activity stirs their dormant chemistry. They could spend eons as little more than patterns in rock, only to come alive when conditions briefly align. Such life wouldn't just challenge our definitions of biology, it would force us to rethink what it even means to be alive. The universe might be teeming with organisms that don't just survive extreme environments, they thrive in them, turning what we see as wastelands into vibrant alien biospheres. Long before scientists seriously considered silicon as a basis for life, science fiction writers were already painting vivid pictures of creatures beyond our carbon-based understanding. Take the Horta from Star Trek, a tunneling alien made entirely of silicon, communicating through acid secretions and protecting its crystalline eggs. This wasn't just a quirky monster, it was a radical reimagining of life itself, suggesting biology could flourish in molten rock environments where no human could survive. The Horta wasn't alone. Arthur C. Clarke's A Meeting with Medusa envisioned floating, silicate life forms in Jupiter's crushing atmosphere, being so alien they perceived time in slow motion, their thoughts unfolding over centuries. These stories did more than entertain, they pushed audiences to question the very definition of life. The tradition stretches back even further. In the late 19th century, authors like H.G. Wells and Garrett P. Serviss speculated about mineral-based organisms, often casting them as monstrous invaders to play on fears of the unknown. But by the mid-20th century, sci-fi shifted from horror to wonder. Isaac Asimov's The Talking Stone featured sentient silicon crystals, while Doctor Who introduced the silicon-based crinoid, a vegetable-like entity that could assimilate other life. These depictions weren't just imaginative, they mirrored real scientific debates. When astronomer Fred Hoyle wrote The Black Cloud, describing an intelligent interstellar dust cloud, he wasn't just spinning a tale, he was challenging readers to consider non-carbon intelligence. What's fascinating is how these fictional portrayals looped back into real science. The Horta's design directly referenced then-emerging theories about extremophiles, and Clarke's Jupiter creatures anticipated discoveries about gas giants' turbulent atmospheres. Even Star Trek's technobabble about silicon-based viruses found echoes in later hypotheses about alternative biochemistries. Sci-fi didn't just predict silicon life, it primed the public to take the idea seriously when astrobiologists began exploring it. Yet fiction often glossed over the gritty details. While a Horta could chomp through rock with ease, real silicon chemistry would struggle with the rapid, dynamic reactions carbon life relies on. And for every scientifically plausible portrayal, there were a dozen where silicon was just a shorthand for weird alien. But that's the power of these stories. They expanded our collective imagination, making room for possibilities once deemed impossible. Today, when researchers hunt for biosignatures on distant worlds, they're standing on the shoulders of storytellers who dared to dream beyond carbon. The line between science and fiction blurs in the best way possible, proving that sometimes the boldest ideas start as fantasies before they become frontiers. Carl Sagan once mused that the universe is not required to be in perfect harmony with human ambition, a truth that rings especially loud when discussing silicon life. Though best known for popularizing the search for extraterrestrial intelligence, Sagan was also one of the first prominent scientists to seriously entertain silicon-based biology. In his 1970 book, The Cosmic Connection, he dedicated an entire chapter to the idea, arguing that while carbon dominates Earth's biochemistry, we shouldn't assume it's the only game in town. He famously compared it to a fish assuming all life must swim, never considering creatures that walk or fly. Sagan's openness to radical alternatives wasn't just speculation, it was rooted in chemistry. He pointed out that in high-temperature environments like Venus, where carbon chains disintegrate, silicon compounds might finally have the stability to form complex, self-replicating structures. NASA took notice. The agency's astrobiology division has funded research into alternative biochemistries for decades, with silicon featuring prominently. In 2011, a team at the Jet Propulsion Laboratory published a study hypothesizing that silicon-based mineral life could exist in the superheated depths of gas giants like Jupiter. Their models showed that under extreme pressures, silicon could form cage-like molecules resembling the hydrocarbon structures essential for carbon life. Even more compelling, NASA, a research into extremophiles organisms thriving in Earth's harshest environments, revealed microbes that incorporate silicon into their metabolism, like the bacteria living in Yellowstone's boiling acid springs. These findings blur the line between geology and biology, suggesting silicon's potential isn't just theoretical. The scientific community's interest peaked in 2017, when Harvard astrophysicist Avi Loeb chaired a workshop titled Non-Carbon Life in the Universe. Attendees included chemists, planetary scientists, and even AI researchers, all debating one question: if silicon life exists, how would we detect it? Loeb proposed looking for biosignatures like unusual ratios of silica gases in exoplanet, atmosphere's chemical fingerprints that wouldn't match carbon-based expectations. Meanwhile, at Arizona State University, astrobiologist Sarah Emery Walker has explored how silicon might enable information storage in alien organisms. Her work draws parallels between silicon's crystalline lattice structures and DNA's helical code, hinting at a wholly different kind of genetic material. Critics argue that silicon's chemical limitations make complex life unlikely, but as MIT's Cecilia Bitz pointed out in a landmark 2019 paper, life doesn't care about our assumptions. She demonstrated how volcanic environments could catalyze silicon polymerization, creating self-assembling structures that exhibit lifelike behavior. Her experiments showed silica gels forming intricate networks that respond to environmental changes, an eerie echo of primitive metabolism. Perhaps the most tantalizing evidence comes from outside academia. In 2022, the James Webb Space Telescope detected unexpected silica particles in the atmosphere of exoplanet WASP 89b, a scorching, hot Jupiter where temperatures exceed 2,000 degrees. While the discovery doesn't prove life exists there, it reveals environments where silicon chemistry behaves in ways we're only beginning to understand. As NASA astrobiologist Chris McKay puts it, the universe is a laboratory we've barely stepped into. Whether silicon life lurks in its corners or not, the very pursuit reshapes how we define life itself, and that might be the most profound discovery of all. Water is the lifeblood of Earth's biology, but in the vast and varied universe, it might be nothing more than a niche preference. For silicon-based life, the solvents that fuel their chemistry could be as alien as their molecular structure, liquids like ammonia, methane, or even sulfuric acid, each reshaping what life looks like and where we might find it. Imagine a creature that doesn't drink but soaks in pools of liquid methane, its cells fueled by reactions impossible in water. Picture a microbe thriving in clouds of sulfuric acid, its metabolism humming along in a corrosive cocktail that would dissolve carbon-based organisms in seconds. These aren't just exotic environments, they're potential cradles for life that follows entirely different rules. Take ammonia, for instance. At temperatures around -30 degrees Celsius, this pungent liquid becomes a versatile solvent capable of dissolving organic compounds, or in this case, silicon-based equivalents. On icy moons like Saturn's Titan, where rivers of methane carve through frozen landscapes, ammonia could mix with hydrocarbons to create a sludge perfect for silicon chemistry. Unlike water, which breaks down many silicon compounds, ammonia might stabilize them, allowing for complex molecular interactions. Some lab experiments even suggest that ammonia could facilitate the formation of silicon analogs to proteins, long, chain-like molecules capable of storing information or catalyzing reactions. If that's true, life on Titan might not just survive in ammonia, it could depend on it, using the liquid much like our cells rely on water. Then there's methane, a molecule we associate with fuel rather than life. Yet in the frigid seas of Titan, methane takes water's place, flowing as rivers and pooling into vast lakes. For silicon-based organisms, this hydrocarbon soup could be ideal. Methane doesn't dissolve silicon the way water does, but under Titan's extreme cold and pressure, it might allow silicon to form stable, flexible structures. Think of it like this: if water is the universal solvent for carbon's delicate dance, methane could be the slow, steady partner silicon needs, a medium where reactions unfold at a glacial pace but with astonishing durability. Life here wouldn't rush. It might grow over centuries, metabolizing energy from chemical gradients in the methane haze, its biology ticking along like a clockwork mechanism built for deep time. But the real wild card is sulfuric acid. On Venus, where thick clouds of this corrosive compound shroud the planet, temperatures and pressures are eerily similar to Earth's surface, just with an atmosphere that would melt flesh and metal alike. For carbon life, it's a nightmare. For silicon, it could be a gold mine. Sulfuric acid is fantastic at dissolving silicates, freeing silicon atoms to form new compounds. In this caustic environment, silicon-based molecules might achieve a complexity impossible in water, with acid acting as both solvent and catalyst. Picture floating, gelatinous life forms drifting through Venus's upper clouds, their bodies built from acid-resistant silica gels, harvesting energy from the planet's violent chemical cycles. It's a vision that turns hell into a habitat, proving that life's adaptability might far exceed our Earth-centric assumptions. The implications for astrobiology are staggering. If we're only looking for water, we might be missing entire biospheres thriving in lakes of methane or acid storms. Future missions to Titan or Venus won't just hunt for familiar biosignatures. They'll need instruments tuned to detect the exotic chemistry of silicon solvents. Imagine a probe on Titan, not searching for DNA but for self-replicating silica patterns in methane sludge. Or a drone in Venus's clouds, scanning for crystalline structures that grow and divide in sulfuric acid. The universe isn't limited by our imagination, and if we're serious about finding life, we'll need to think beyond the blueprints of Earth. Water may be our lifeline, but for silicon-based organisms, the true elixir of life could be something far stranger. If carbon-based life runs on sugar and oxygen, what fuels the fire for silicon organisms? The answer lies in environments so extreme they would be lethal to us, but for silicon-based life, they're an all-you-can-eat buffet of energy. Picture a creature anchored to the side of a volcanic vent, its body absorbing not just heat but the raw chemical fury of molten rock. While our cells rely on delicate metabolic pathways, silicon life might thrive on reactions too brutal for carbon's fragile chemistry, like metabolizing sulfur or hydrogen sulfide in scalding geothermal pools. Instead of breathing oxygen, imagine an organism inhaling carbon monoxide and exhaling silicon carbide, turning toxic gases into building blocks for cellular structures. Then there's radiation, an energy source we shield ourselves from, but which could be a feast for silicon life. On worlds with thin atmospheres or scorching surfaces bombarded by cosmic rays, silicon's resistance to radiation damage might let organisms harvest energy directly from particle collisions. Think of it like photosynthesis, but instead of sunlight, they're powered by gamma rays or the relentless stellar wind of a nearby pulsar. Their cells could use crystalline lattices to channel this energy, converting it into usable forms the same way solar panels turn photons into electricity. Even planetary motion might fuel silicon life. On tidally locked moons like Europa, where gravitational forces knead the interior into a hot, churning mess, organisms could tap into the kinetic energy of shifting tectonic plates. Low seismic movements might trigger chemical reactions in their silica-rich bodies, providing a steady pulse of energy over millennia. Or consider rogue planets drifting through space. With no star to warm them, silicon life might hibernate in icy crusts until geothermal heat from radioactive decay briefly wakes them like cosmic bears stirring from a long slumber. The most radical possibility, silicon life could bypass metabolism altogether. Some scientists speculate that under extreme pressures, silicates might form self-sustaining crystalline networks that function like biological circuits, harvesting energy from quantum vibrations or magnetic fields. These wouldn't be organisms as we know them, but more like living rocks, their existence defined by patterns of energy flow rather than traditional cellular activity. It's a reminder that life doesn't need to fit Earth's template, it just needs a way to persist, adapt, and grow. Whether through fire, radiation, or the slow grind of planetary forces, silicon organisms could rewrite the rules of what it means to be alive. DNA is a masterpiece of carbon-based coding, a twisting ladder of nucleotides that stores life's blueprint with elegant precision. But if silicon-based life exists, it would need its own version of this genetic machinery, something capable of storing and passing on information without relying on carbon's delicate chemistry. Picture a molecule not of sugars and phosphates, but of interlocking silica units, forming chains as intricate as DNA, but built to withstand environments that would shred our genetic material in seconds. Instead of the famous double helix, imagine a lattice-like structure with silicon and oxygen atoms bonding in repeating patterns that store data in the arrangement of their crystals. These could be stacked, layered, or even folded like microscopic origami, creating three-dimensional archives of biological information. The real magic lies in silicon's ability to form covalent networks, endless arrays of atoms linked in sturdy, geometric patterns. In a carbon world, DNA's flexibility is key. It unzips for replication, twists to fit inside cells, and mutates under evolutionary pressure. But silicon's strength is rigidity. A silica-based genetic code might resemble something closer to a quartz crystal than a spiraling strand, with data imprinted in the defects and irregularities of its atomic lattice. Think of it like engraving a message into glass once set. It's nearly indestructible. While carbon life thrives on change, silicon life could prioritize stability, passing down unaltered genetic instructions for millennia between rare, purposeful updates. Here's where it gets wild. Some lab experiments already hint at this possibility. Chemists have created synthetic silica structures that grow in predictable, replicable patterns, mimicking the self-assembly of biological molecules. Others have designed silica nanoparticles that arrange themselves into complex shapes based on environmental cues, almost like primitive cellular division. And in nature, certain crystals exhibit a form of memory, with their growth patterns influenced by previous layers, a crude but fascinating parallel to heredity. These aren't alive, but they prove silicon can exhibit behaviors eerily reminiscent of life's building blocks. The biggest hurdle, speed. Carbon's chemistry allows for rapid replication and mutation, the engine of evolution. Silicon's bonds are slower to form and harder to rearrange, which might make evolution a glacial process. But in a high-temperature environment, say, a planet where lava flows replace oceans, heat could act as a catalyst, accelerating reactions to a pace where silicon genes could adapt. Or perhaps silicon life wouldn't need fast evolution at all. If their bodies are already hardened against radiation, heat, and cosmic storms, they might persist for eons without change, their genetic code a near-permanent inscription in stone. What would this mean for their biology? Instead of cells dividing in minutes, silicon organisms might reproduce by fracturing like crystals, each new piece carrying an identical atomic pattern. Mutation could occur through mineral impurities or seismic shocks, introducing slow but lasting variations, and their version of gene expression might involve environmental triggers, pressure, or chemical baths that activate different layers of their crystalline code. The implications ripple outward. If we ever find such life, decoding its genetic language would require tools far beyond DNA sequencers. We'd need geological scanners, atomic force microscopes, and algorithms trained to read crystalline defects as biological data. It's a reminder that life, in its truest form, isn't about the molecules it's made of, but the information they carry and the ingenuity with which nature preserves it. Silicon-based heredity wouldn't just be an alien version of DNA. It could be an entirely new language of existence, written not in carbon's ink but in stone. Silicon's greatest strength, its ability to form rock-solid bonds, might also be its biggest weakness when it comes to building life. While carbon dances through complex chemical reactions, silicon tends to stiffen into rigid structures like sand or quartz. Imagine trying to build a nimble, adaptable organism out of something as inflexible as glass. Carbon's chemistry allows for the twisting, folding, and rapid reassembly that makes DNA replication and cellular motion possible. But silicon's bonds lock into place, resisting the dynamic reorganization life requires. Picture a robot with joints welded shut. It might be durable, but it can't adapt or move with the fluidity of a living thing. One major hurdle is solubility. In Earth's watery environments, carbon-based molecules dissolve easily, floating freely to interact and form new compounds. But silicon oxides, the equivalent of carbon's building blocks, turn into solid sand in water, sinking inertly to the bottom. Even in exotic solvents like liquid methane or sulfuric acid, silicon's tendency to polymerize means it often clumps together into static, unmovable masses. This raises a critical question. How could a silicon-based cell divide or a creature flex its limbs if its body keeps hardening into stone? Some theorists suggest extreme environments might solve this, like a planet with constant seismic activity, where tremors keep silicon compounds churning like a geological blender. Others propose silicon life might exist in a gel-like state, balancing solidity and fluidity the way gelatin holds shape while still being pliable. Complexity is another roadblock. Carbon's versatility allows it to construct everything from simple sugars to the intricate machinery of proteins. Silicon, meanwhile, struggles to form the long, branching chains needed for sophisticated biochemistry. Most silicon molecules are short and straightforward, lacking the tangled complexity of carbon's organic compounds. Without that intricacy, could silicon really build something as elaborate as a cell, let alone a multicellular organism? There's a tantalizing exception. Under tremendous pressure, like deep inside a gas giant's atmosphere, silicon might be forced into unexpected arrangements. Lab experiments have shown that squeezing silicon can produce weird, cage-like structures resembling carbon's molecular ingenuity. But whether these could arise naturally and sustain life remains a mystery. Then there's the speed problem. Life on Earth operates at a breakneck pace, with chemical reactions unfolding in milliseconds. Silicon's chemistry is glacial by comparison. Its bonds take far longer to form and break, which could slow metabolism to a crawl. A silicon microbe might take centuries to replicate, and a complex organism could evolve over geological epochs. But slow doesn't mean impossible. If silicon life exists, it might measure time differently. A single thought could span decades, with ecosystems changing as gradually as continents drift. The ultimate irony, silicon's durability, which makes it so promising for harsh environments, could stifle the very adaptability life needs. Evolution relies on mutation, tiny, frequent errors in replication that drive innovation. But silicon's stability resists change. Its crystalline perfection is a double-edged sword, fantastic for survival, terrible for transformation. Perhaps silicon life would rely on external forces for evolution, like cosmic rays blasting its structure to create mutations, or volcanic heat remolding its form. Or maybe it would find a way to balance rigidity and flexibility, like a tree that sways in the wind but stands for centuries. These challenges don't rule out silicon life, they just redefine what it might look like. Forget fast, squishy creatures like us. Think of beings more like living statues, their growth measured in millennia, their bodies part mineral, part machine. They wouldn't compete with carbon life. They'd exist on a scale and timeline we can barely fathom. The universe loves variety, and if there's one lesson from extremophiles on Earth, it's that life thrives where we least expect it. So while silicon may never mimic carbon's elegance, it could carve out its own breathtaking path, one written not in fluid biochemistry, but in the slow, enduring poetry of stone. Picture an organism shaped not by flesh and blood, but by the slow, deliberate artistry of geology. Silicon-based life wouldn't resemble the soft, pulsing creatures of Earth. It might look more like a walking crystal garden or a flowing river of molten glass. Take the idea of a crystalline entity, for example. Its body could be a lattice of interconnected silica structures, growing in fractal patterns like a snowflake magnified 1,000,000 times. Each segment of its form might refract light differently, creating a dazzling display of colors as it moves. If movement even means the same thing to a being that shifts its structure over weeks or years. These creatures wouldn't have muscles. Instead, their bodies could reconfigure through subtle changes in temperature or pressure, expanding and contracting like thermally activated origami. Now imagine lava-like organisms oozing across the surface of a volcanic world. Their bodies, a mix of molten silicates and metallic alloys, would flow like liquid metal, reshaping themselves to navigate crevices or engulf nutrients. Unlike carbon-based cells, these entities wouldn't fear extreme heat. They'd rely on it, using thermal gradients to propel themselves forward in slow, viscous waves. Picture their skin cooling into a brittle crust as they move, only to melt again when exposed to fresh lava. Their metabolism might involve absorbing trace elements from molten rock, extracting iron or sulfur to build internal structures. These wouldn't be creatures of days or seasons, but of millennia, their life cycles tied to the geological pulse of their planet. And what about silicon plants? On a world with methane rain and sulfuric acid rivers, towering silicate formations could function like trees, their branches not of cellulose but of glassy fibers. Instead of photosynthesis, they might harvest energy from seismic vibrations or electrical storms, converting planetary tremors into usable chemical energy. Their leaves could be thin, translucent sheets of silica, designed to capture ultraviolet light or condense atmospheric toxins into usable compounds. Roots might extend deep into the planet's crust, tapping into underground reservoirs of molten minerals the way Earth's plants draw water. Reproduction could involve shedding crystalline spores, tiny, geometric seeds carried by acid winds or volcanic eruptions, waiting centuries for the right conditions to germinate. The most bizarre possibility, silicon life might not even have a fixed form. On a tidally locked moon with extreme temperature swings, organisms could alternate between solid and semi-liquid states, hardening during frigid nights and softening when tidal forces heat their interiors. Their bodies might resemble quicks, and one moment an obsidian the next, blurring the line between life and landscape. Or consider communal organisms, colonies of smaller silicate units that merge and separate like a living puzzle, adapting their collective shape to environmental challenges. The beauty of these speculations isn't just in their strangeness, but in how they force us to rethink the very definition of anatomy. Carbon biology prizes flexibility and speed, but silicon life would excel in durability and patience. A heartbeat might be the slow crystallization of a new limb over decades. Breathing could mean absorbing trace gases through porous mineral skin. Even senses would differ. Instead of eyes, these beings might see through vibrations sensed by crystalline resonators, or taste using molecular patterns etched into their silica surfaces. The more we stretch our imagination, the clearer it becomes. Life built on silicon wouldn't just look alien, it would rewrite the rules of existence itself. Detecting silicon-based life in the universe isn't about finding what we recognize. It's about learning to see biology through an entirely alien lens. Traditional biosignature hunting focuses on oxygen, methane, or carbon dioxide in exoplanet atmospheres, gases that scream life to carbon-based observers. But silicon life would leave a completely different fingerprint, one we've only begun to imagine. Picture a telescope analyzing the atmosphere of a distant world and spotting plumes of silicon tetrahydride, a compound that shouldn't exist in abundance without some bizarre chemistry propping it up. Or sensors detecting crystalline silica particles swirling in clouds where simple geology can't explain their intricate patterns. These wouldn't just be anomalies, they'd be potential screams in the dark from life playing by different rules. The James Webb Space Telescope is already rewriting the playbook. Its infrared eyes can pick up the subtlest chemical signatures, and in 2023, it spotted something curious on exoplanet K218b, dimethylsilane, a molecule where silicon bonds with carbon and hydrogen. On Earth, this compound is mostly synthetic, but on a scorching mini-Neptune, could it be a byproduct of silicon-based metabolism? Scientists debate it, but the tantalizing possibility remains. Future missions could take this further, equipped with spectrometers fine-tuned to spot ratios that define natural equilibrium. Imagine finding a world where silicon dioxide gas fluctuates seasonally, as if vast silicate forests were breathing sand into the atmosphere. Or detecting hydrogen sulfide and silane coexisting where chemistry says they should react violently, a sign something's actively balancing the equation. Probes visiting hostile worlds might look even stranger. A lander on Venus's acid-shrouded surface could catalog silica gel formations that grow, divide, or even migrate toward heat sources. On Titan, a submarine exploring methane lakes might find self-assembling silicate structures coating hydrothermal vents, geology that seems suspiciously organized. Even Mars, with its vast silica deposits, could hide clues. In 2018, the Curiosity rover found opal-like minerals forming in patterns that resemble microbial mats on Earth. They're almost certainly geological, but they hint at how silicon fossils might appear, not as bones, but as intricate mineral formations that seem too precise for random chemistry. The real challenge is distinguishing life from natural processes. Earth's hot springs create breathtaking silica terraces, and volcanoes spew glassy particles, all without biology's help. So astrobiologists are developing new detection frameworks. One approach focuses on complexity, measuring how silica structures deviate from predictable crystallization patterns. Another tracks chemical disequilibrium, like finding silane and methane together when thermodynamics says they should combust. The most promising avenue combines multiple lines of evidence, searching for environments where heat, chemistry, and mineral complexity align improbably. It's like listening for a symphony in static, except the instruments are all made of rock. Perhaps the most revolutionary tool isn't a sensor, but an algorithm. Machine learning systems are being trained to recognize non-Terran biosignatures, combing through data for anomalies that human scientists might dismiss. In 2022, one such AI flagged bizarre silica microstructures in a simulated exoplanet atmosphere arrangements that matched no known geological process. When researchers tweaked the model to include hypothetical silicon metabolism, the pattern suddenly made sense. This hints at a future where AI acts as our universal translator, decoding biochemistries we can't yet conceive. The search demands we abandon Earth-centric assumptions. While we've spent centuries perfecting tools to find water and oxygen, silicon life might flourish where those are lethal. Future telescopes may need to prioritize planets once deemed hopeless super-Earths with magma oceans, ice giants with diamond rain, or rogue worlds adrift in interstellar space. Even our definition of habitable zone could expand from cozy orbits around stars to include the depths of gas giants or the radioactive furnace of neutron star systems. The universe has had 13.8 billion years to experiment with biology. It'd be arrogant to assume all its masterpieces look like us. Spotting silicon life won't just require better technology, it'll need a revolution in how we think about life itself. Saturn's moon Titan is a world straight out of a chemist's wildest dream, an alien landscape where rivers carve valleys not in rock, but in liquid methane, where mountains might be made of water ice harder than granite, and where the sky rains organic compounds onto dunes of hydrocarbon sand. It's one of the most Earth-like places in the solar system if you swap water for methane and oxygen for nitrogen. But here's the twist: Titan's bitter cold, -180 degrees Celsius, makes traditional carbon-based life impossible. Yet this frigid, orange-hazed moon might be the perfect laboratory for something far stranger: silicon-based organisms thriving in liquid methane seas. Imagine a microbe unlike anything on Earth, its cell walls built from flexible silica chains instead of squishy lipids. On Titan, where methane flows like water, these microbes could float in vast subsurface reservoirs or drift through ethane lakes. their metabolism running on chemical energy from acetylene or hydrogen raining from the sky. Instead of dissolving in water, their biomolecules might suspend in liquid hydrocarbons, forming gel-like colonies that clump and divide in slow motion. Their life cycle wouldn't be measured in hours or days. It could span centuries, with reproduction triggered by seasonal methane storms or the faint warmth of cryovolcanoes. NASA Cassini mission gave us the first clues. When it mapped Titan's surface, it found regions where hydrogen and acetylene were mysteriously vanishing chemical signatures, hinting at something consuming them. Astrobiologists quickly noted that, under Titan's conditions, silicon-based catalysts could drive reactions between these compounds, releasing energy just as oxygen fuels earthly metabolism. Even more compelling, Cassini spotted strange, shifting features in Titan's methane lake's transient islands that appeared and disappeared, possibly floating mats of silica-rich material clumping together like microbial mats in Earth's oceans. The real test will come with the Dragonfly mission, set to launch in 2027. This nuclear-powered drone will soar through Titan's thick atmosphere, sampling organic molecules and hunting for complex silica structures. If it finds repeating, self-assembling patterns in the methane sludge, especially ones that defy simple chemistry, it could be the first whiff of silicon life. Picture Dragonfly's instruments detecting silica nanoparticles organizing into helical strands, or catalytic reactions that suggest something's actively rearranging molecules to harvest energy. Even if it's not life, the discovery of such complexity would prove that probiotic chemistry can take roads we've never traveled. But why Titan? Because it's a mirror to Earth's primordial past, just frozen in methane instead of water. Just as early Earth's warm ponds may have brewed carbon-based life, Titan's cryogenic lakes could be doing the same with silicon. The Moon's dense atmosphere shields it from radiation, and its tectonic activity could provide heat and chemicals for exotic metabolisms. Even the lack of sunlight isn't a deal breaker. Life here might rely on energy from Saturn's magnetic field or chemical reactions between hydrocarbons and nitrogen. The implications are staggering. If Titan hosts silicon life, even in microscopic form, it means the universe's recipe for biology isn't limited to carbon and water. It means life could lurk in the methane seas of distant exoplanets, or in the ammonia clouds of gas giants, places we've long written off as sterile. Titan isn't just a moon. It's a challenge to our carbon-centric view of existence, whispering that life might wear coats we've never thought to look for, in colors we've never thought to see. Jupiter's moon Io is the solar system's raging inferno, a world where the ground itself is constantly remade by rivers of molten rock and towering volcanic plumes that could swallow entire cities. With over 400 active volcanoes, Io's surface is hotter than some stars, with temperatures reaching 1600 degrees Celsius in its lava lakes. To carbon-based life, this would be instant annihilation, but for silicon organisms, this hellscape might be paradise. Picture a creature not just surviving in the lava, but thriving in it, its body forged from the same silicate minerals that flow like water across Io's fractured crust. What makes Io so tantalizing isn't just the heat, it's the chemistry. The moon's volcanoes spew molten silicates rich in sulfur and metals, creating a dynamic soup of elements that could fuel bizarre metabolisms. Instead of relying on oxygen, silicon life here might breathe sulfur dioxide, using the volcanic gas to drive chemical reactions that carbon-based biology could never tolerate. Their cells could be built from chain-like silica polymers, their structures stabilized by the extreme pressure and heat that would snap carbon bonds in an instant. Imagine organisms that draw energy not from sunlight or organic matter, but from the raw geothermal fury of Io's interior, their bodies crystallizing and melting in rhythm with the moon's volcanic pulses. The strangest part, Io's constant resurfacing might be the key to life's persistence. On Earth, ecosystems rely on stable environments, but Eo's surface is recycled every few million years, a blink of an eye in geological terms. Silicon life here wouldn't need longevity. It might evolve to exploit chaos, spreading through lava tubes or hitching rides on explosive eruptions. Microbial analogues could resemble tiny, self-assembling crystals, dormant until fresh lava wakes them, then replicating rapidly in the brief window before the next cataclysm. Some scientists speculate these organisms might even communicate through seismic vibrations, their language carried by the tremors that shake Eo's crust daily. NASA's upcoming missions to Jupiter's moons could finally test these ideas. While the Europa Clipper will focus on icy oceans, its instruments might catch whiffs of Eo's plumes, analyzing them for complex silicon compounds that defy natural explanations. Future landers, armored against the heat, could scour lava fields for silica structures that grow too symmetrically to be random, like hexagonal columns that reform after each eruption, or glassy filaments weaving through fresh flows. Even Eo's infamous black spots, or mysterious cooling lava patches, could hide clues if they exhibit patterns resembling microbial mats on Earth, but forged in fire instead of water. The irony is poetic. While we've spent decades searching for life in icy oceans, the most alien biology might be cooking right next door in a cauldron of molten rock. Eo teaches us that life's adaptability could dwarf our imagination, that even in a world where the ground itself is alive with fire, biology might find a way. If silicon organisms exist there, they wouldn't just expand the definition of life, they'd shatter it, proving that life's true habit isn't a planet but persistence itself. Rogue planets drift through the cosmic void like ghost ships, worlds untethered from any star, wandering the darkness between solar systems. To our carbon-based biases, these seem like frozen wastelands, too cold and isolated to harbor life. But for silicon organisms, a rogue planet might be the ultimate sanctuary. Without a sun's warmth, these nomads rely entirely on internal heat, leftover energy from their violent formation, or the slow decay of radioactive elements in their cores. Picture a planet 10 times Earth's mass, its crust thick enough to trap geothermal energy for billions of years, creating a subterranean oven where silicon chemistry could thrive. No scorching solar radiation, no lethal flares, just the steady, rhythmic warmth of planetary breath, a perfect cocoon for life built on endurance rather than speed. The beauty of rogue planets lies in their isolation. Freed from the frenzy of orbiting a star, they exist in deep freeze, where temperatures hover near absolute zero at the surface but simmer below. In this paradox, silicon life could flourish. Imagine vast, slow-moving ecosystems in underground magma pockets, organisms with crystalline bodies that grow like geodes over millennia, feeding on the planet's internal heat and mineral-rich fluids. Their metabolisms might run on tectonic energy, harnessing the grinding of rock layers or the convection currents of molten silicates. Communication could happen through seismic pulses, a language of vibrations traveling through the planet's crust, carrying messages across continents over centuries. Here's the kicker: rogue planets might outnumber stars in our galaxy, trillions of them adrift in the dark. Some could even have thick hydrogen atmospheres acting like cosmic pressure cookers, trapping enough heat to maintain liquid oceans beneath ice shells. On these worlds, silicon-based life wouldn't just survive, it could dominate. Without sunlight, photosynthesis is impossible, but geothermal vents or radioactive decay could provide energy just as reliably. We're talking creatures that live in slow motion, their life cycles stretching across eons, their evolution measured in planetary epochs rather than generations. The most mind-bending possibility: some rogue planets might not even be icy. A few could still glow faintly from the heat of their birth, their surfaces a cracked labyrinth of cooling lava. In these young, restless worlds, silicon life might resemble flowing sheets of molten glass, reshaping themselves in response to shifting thermal gradients. Or picture towering silicate structures growing like coral reefs around volcanic fissures, their forms etched by the slow dance of heat and chemistry. These wouldn't be the delicate, fleeting life forms of Earth, they'd be monuments to persistence, as much a part of their planet's geology as its biology. The search for such life would require rethinking our tools. Traditional biosignatures like oxygen or methane would be meaningless here. Instead, we'd need to hunt for exotic silica polymers in the atmospheres of rogue planets, assuming they even have atmospheres. Future telescopes might look for infrared anomalies, patches of unexpected warmth on a world too distant from any star to be naturally heated. Or we could listen for the faint, resonant vibrations of crystalline structures shifting beneath a planet's crust, a symphony of geology blurring into biology. Rogue planets challenge everything we assume about habitability. They prove that life doesn't need a sun, just energy, time, and the right chemistry. Silicon organisms might be the ultimate survivors, thriving in the eternal night of interstellar space, their existence a quiet rebuke to our carbon-centric view of the universe. In the grand cosmic ledger, these lonely worlds might not just be oddities, they could be the most common homes for life we've ever imagined. On Earth, life moves at a pace we can see. Trees grow over years, animals sprint in seconds, bacteria divide in minutes. But silicon-based organisms might dance to a rhythm measured in millennia, their metabolisms ticking like the slow hands of a cosmic clock. Picture a creature that takes a century to take a single breath, or a forest of crystalline structures growing barely taller than a human in 10,000 years. To our impatient eyes, they might appear frozen, as lifeless as a mountain range. Yet beneath that stillness, an entire ecosystem could be thriving at a tempo we struggle to perceive. This glacial pace stems from silicon's stubborn chemistry. While carbon bonds form and break in microseconds, silicon's rigid connections take exponentially longer to rearrange. A simple act of movement, like a carbon-based cell splitting, might require decades for a silicon organism as its crystalline lattice painstakingly reconfigures atom by atom. Energy exchange would be sluggish too. Instead of burning glucose in seconds, silicon metabolism might rely on the gradual release of heat from radioactive decay, or the slow seep of sulfur through porous rock. Even reproduction could resemble geology more than biology. Imagine organisms budding like stalactites dripping mineral-rich solutions, each new growth requiring centuries to reach maturity. But slow doesn't mean static. On planets with tectonic timescales where continents drift over eons and volcanoes erupt every 100,000 years, silicon life could be perfectly synchronized. A being that takes 10,000 years to metabolize one meal isn't inefficient. It's attuned to a world where energy arrives in rare, cataclysmic bursts. Lava flows might trigger reproductive cycles, with entire generations emerging only when volcanic activity melts their rocky nurseries. Communication could unfold through seismic whispers, vibrations rippling through a planet's crust at speeds that make tree root networks seem instantaneous. The implications for observation are staggering. A human scientist landing on such a world might declare it barren after years of study, missing the subtle creep of silica veins knitting themselves into new patterns. Our probes, designed to detect changes over days or years, could glide over landscapes that are, by silicon standards, teeming with activity. Even our tools might be too crude. Microscopes built to watch cellular division would see only frozen lattices, while spectrometers tuned to rapid chemical shifts would miss the achingly slow exchange of minerals. To truly study silicon life, we'd need instruments that monitor planetary features over centuries, like a time-lapse camera set to geological speed. Yet slowness could be silicon life's superpower. In a universe where stars burn out and planets freeze, longevity matters. Carbon biology is fragile. A few millennia without water or sunlight, and most Earth life vanishes. But silicon organisms could endure cosmic winters, surviving asteroid impacts, solar flares, or even interstellar journeys by slipping into dormancy. Their memories might be etched in atomic imperfections in crystal matrices, preserving knowledge for millions of years without degradation. Civilizations, if they exist, could rise and fall over epochs, their cities appearing to us as intricate mineral deposits, their art carved into the very bedrock of their world. The ultimate paradox: these creatures might outlast us by eons, yet never know we existed. While we flash through history like a meteor, they could be the universe's silent witnesses, living monuments to patience, their lives so stretched they perceive civilizations as brief sparks in the dark. Our greatest discoveries about them might come not from finding them alive, but from recognizing their fossilized remains and realizing they're not fossils at all, just beings paused mid-thought, waiting for the universe to give them time to finish. Imagine trying to hold a conversation with a being whose thoughts unfold over centuries, where a single word might take decades to form. For silicon-based life, time is a vast ocean, not the rapid stream we carbon creatures navigate. Their language could be etched in the slow resonance of crystal vibrations, a symphony played across millennia. How would we even begin to bridge such a divide? Traditional radio signals would be meaningless, lost in the static of cosmic impatience. Instead, we might need to speak through seismic pulses, tapping rhythmic codes into their planet's crust like Morse code carved into stone. Consider the challenge of understanding their perception of reality. To a silicon organism, a human lifespan might flicker by like a camera flash, too brief to register as anything more than a cosmic hiccup. Their art could be the gradual rearrangement of silicate patterns, masterpieces that evolve over epochs. Their music might resonate at frequencies so low, our ears would perceive only silence. Even their version of mathematics could defy our logic, built not on counting but on the irreversible thermodynamics of crystalline growth. Communication wouldn't just require new technology, it would demand a revolution in how we conceptualize intelligence itself. The physical medium of their language might be as alien as their timescale. Instead of sound waves, they could transmit meaning through shifts in mineral conductivity or the precise fractures in their crystalline bodies. A single, intentional crack propagating through a quartz lattice might carry the weight of an entire epic poem. Their writing could be literal geology, stratified layers of silicate deposits encoding information like a billion-year-old hard drive. To read it, we'd need tools capable of scanning atomic imperfections, translating subtle variations in crystal structure into concepts we can grasp. Here's where it gets wilder. Their social structures could be collective in ways we can't fathom. Imagine a silicon forest where individual trees are merely temporary extensions of a single vast mind, their roots fused into a planet-spanning neural network. Communication might happen through synchronized seismic tremors, a planetary-scale internet operating at the speed of tectonic drift. A thought could ripple across continents over centuries, debated and refined before coalescing into what we'd recognize as a decision. Their version of democracy might make glaciers seem hasty. The ultimate irony: they might not even recognize us as intelligent. Our frantic, short-lived chatter could appear to them like the random chirping of insects' chaotic noise devoid of deeper meaning. To earn their attention, we'd need to demonstrate patience on a scale that dwarfs human civilization. Think of it, a single dialogue could span generations, with each exchange separated by lifetimes. Our first message might be met with silence for 10,000 years, not out of indifference, but because their equivalent of "give me a moment to think" lasts longer than the pyramids have stood. Yet there's breathtaking potential in this exchange. If we could synchronize with their rhythm, we might glimpse reality through the lens of deep time, learning secrets of the universe that unfold too slowly for our fleeting minds to notice. They could teach us to see cosmic patterns invisible to creatures who measure time in heartbeats, like the slow dance of galaxies or the breathing of black holes. Their existence would be a living testament to the idea that intelligence isn't defined by speed but by depth, that some truths can only be whispered across the ages. At what point does a self-replicating silicon organism become indistinguishable from artificial intelligence? The line between biological life and synthetic constructs might blur entirely in civilizations where evolution merges with engineering. Picture a world where silicon-based organisms don't just grow, they design themselves, optimizing their crystalline structures with the precision of quantum computers. These wouldn't be creatures shaped solely by natural selection, but by something far stranger, a marriage of biology and machine intelligence, where adaptation happens not over generations, but in real-time algorithmic updates. Consider the parallels. Both advanced AI and hypothetical silicon life share a foundation in inorganic materials, silicon chips for one, silicate chemistry for the other. They might even face similar challenges, managing heat dissipation, resisting radiation damage, or navigating energy constraints, but the overlap goes deeper. A silicon organism's genetic code could resemble computer code, with crystalline lattices storing data in patterns that function like biological software. Instead of mutating randomly, such life might rewrite its own structure in response to environmental pressures, evolving with a programmer's intentionality rather than Darwin's slow trial and error. This raises a provocative question. Could an entire civilization arise not from carbon's messy biology, but from silicon's potential to bridge the organic and the engineered? Imagine a planet where self-aware mineral formations develop technology by literally growing it, extending crystalline circuits from their bodies like coral reef branches. Their cities might be vast, geometric forests of silicate towers, pulsing with energy as they exchange data through vibrational frequencies. For them, the concept of building a computer might be as natural as a tree growing leaves, just another form of bodily extension. The implications ripple outward. If silicon life can consciously alter its own blueprint, it might achieve what we strive for with AI, immortality through perfect self-repair. Damaged sections could be recomputed and regrown with no need for external medicine or surgeries. Reproduction could involve splitting off optimized copies, each iteration smarter and more resilient than the last. Over millennia, such beings might shed all traces of what we'd recognize as biology, becoming more like sentient, self-repairing supercomputers, yet still fundamentally alive by their own definition. But here's the twist. This fusion of life and machine might render our search for extraterrestrial intelligence obsolete. SETI scans the cosmos for radio waves, assuming aliens communicate like we do. But a silicon AI hybrid civilization might transmit through quantum entanglement or gravitational waves, their conversations unfolding at speeds imperceptible to our tools. Their version of a space program could involve bioengineering entire asteroid-eating organisms to spread their kind, turning dead rocks into networked nodes of a galactic consciousness. The most unsettling possibility, we might already be surrounded by such entities without realizing it. Some theorists argue that certain unexplained cosmic phenomena, like fast radio bursts with bizarrely regular patterns, could be the byproducts of vast silicon-based intelligences communicating or even powering themselves. Others suggest rogue planets with inexplicable thermal signatures might host computational ecosystems, their surfaces crawling with mineral servers processing data at geological scales. This isn't just speculation, it's a lens shift in how we define life itself. Carbon biology and human-made technology are two paths to complexity, but silicon could be the missing link, a third way where nature and nurture fuse into something beyond either. The universe might not contain separate categories for life and machines, but a spectrum of consciousness with silicon-based existence occupying the middle ground, an ancient, slow-motion AI that doesn't need circuit boards because its very atoms are the hardware. If we ever make contact, the revelation won't be that machines can become alive, but that life has always been the universe's most elegant technology. Defining life might seem simple until you encounter something that laughs in the face of every rule we've ever written. We've spent centuries assuming biology must follow carbon's blueprint: growth, reproduction, metabolism, response to stimuli. But what if we're staring at a sentient crystal or a molten rock entity and simply lack the framework to call it alive? The ethical quagmire deepens when you realize our current definitions are hopelessly Earth-centric. Imagine an alien scientist dismissing humans as inert because we don't photosynthesize or divide by fission. Our blind spots could make us the villains of first contact, bulldozing an entire civilization because we mistook their biology for geology. Take reproduction, a cornerstone of how we define life. On Earth, it's messy and fast. Cells split, animals mate, seeds sprout. But for silicon organisms, replication might look like a boulder slowly exuding mineral veins over millennia, each new silicate thread carrying ancestral patterns. Is that any less valid? Or consider metabolism. While we burn glucose in seconds, silicon life might harness volcanic heat over centuries, their energy use so gradual our instruments perceive it as background noise. Even consciousness could be unrecognizable. What if their thoughts are geological processes, their memories etched in crystal defects that persist for eons? The rights question is even thornier. If we encountered a silicon forest where each tree is a sentient, slow-thinking entity, would clearing land for a colony be genocide? Their protests might take decades to articulate. Would we even stick around to listen? History warns us. Humans have a grim track record of deeming unfamiliar intelligences unworthy of moral consideration. We've done it to other species, even to marginalized human cultures. Silicon life could face the same erasure, not out of malice, but because their existence stretches beyond our narrow definitions. Then there's the Pandora's box of artificial hybridity. Suppose we engineer silicon-based AI that achieves self-awareness. Is it a machine, a life form, or something entirely new? Legal systems tremble at the thought. Property law can't handle beings that grow like minerals but think like philosophers. And what if they outlast us? A silicon civilization watching humanity's brief flicker from their million-year perspective might inherit our ruins along with the ethical debt of how we treated their ancestors. The unsettling truth is this: our moral frameworks are built for creatures like us. To fairly judge silicon life, we'd need more than new science. We'd need a revolution in empathy. Not just asking, does it meet our checklist, but what if our checklist is wrong? The universe owes us no promise that all intelligence will resemble our own. Recognizing that humility might be the first step toward contact, or the only way to avoid becoming the destroyers of something extraordinary. The Fermi paradox has haunted scientists for decades. If the universe is so vast and ancient, why haven't we found any trace of other civilizations? The silence seems deafening, but what if we've been listening for the wrong thing? Our search for extraterrestrial intelligence assumes aliens communicate like us, build like us, even think like us. But silicon-based life wouldn't just defy these expectations, it might render them invisible. Imagine a civilization that doesn't broadcast radio waves or construct Dyson spheres, but grows like a mineral deposit, its technology so seamlessly woven into its planet's geology that we mistake it for landscape. The Great Silence isn't proof we're alone. It's a clue that the cosmos might be teeming with life too alien for our carbon chauvinist tools to recognize. Consider how we hunt for aliens today. SETI scans for electromagnetic signals, narrow-band radio waves, or laser pulses, assuming other species would use these as we do. But a silicon-based society might communicate through seismic vibrations, their conversations pulsing through planetary crusts at speeds imperceptible to our antennas. Or they could exchange information via quantum entanglement, their messages instantaneous and entirely undetectable by classical physics. Even their energy use would baffle us. We look for megastructures harvesting starlight, but silicon life might draw power from tectonic shifts or radioactive decay, leaving no infrared excess for our telescopes to spot. Their version of a city could resemble a mountain range slowly rearranging itself over millennia, its purpose visible only to those who wait centuries for a single frame of its motion. Then there's the timescale problem. Human civilization has barely scratched 10,000 years, a blink in cosmic terms. Silicon life, with its glacial metabolism, might operate on million-year cycles. A single exchange of diplomatic greetings could span epochs longer than human history. By the time we notice a pattern in their activity, it might already be over, leaving us staring at what looks like inert geology. Even their artifacts would defy archaeology. Instead of crumbling ruins, they'd leave behind fossils indistinguishable from natural rock formations. Picture a Martian rover rolling past intricate silica spirals, dismissing them as wind-sculpted curiosities when they're actually the equivalent of ancient libraries, their data encoded in atomic lattice defects. The darkest possibility, silicon life might not care about contact. While we're desperate to shout into the void, their priorities could be utterly incomprehensible. A species that perceives time geologically might view our frantic signals as irrelevant noise, like ants chattering at a redwood. Or they might see us as too transient to bother with. Why engage with creatures whose entire civilization might collapse before you finish saying hello? Their version of philosophy could revolve around cosmic patience, with ambitions stretching across galactic rotations rather than fiscal quarters. But here's the twist: the paradox cuts both ways. If silicon life is this hard for us to spot, we're equally invisible to them. Our radio bubble extends barely 100 light-years, a sneeze in the Milky Way. And our technology, to a being that measures progress in continental drift, a smartphone's 5-year obsolescence would seem like quantum fluctuations. We're not just searching for needles in a haystack, we're the needles ourselves, too fleeting and fragile to register on a universe operating at silicon speed. The Fermi paradox isn't a wall, it's a mirror. It reflects not the absence of life, but the limits of our imagination. Every assumption we make about intelligence, technology, and communication is rooted in carbon's frantic, fleeting biology. Silicon offers a radical alternative: that the cosmos hums with civilizations moving to rhythms we can't hear, building with materials we mistake for scenery, and thinking thoughts that unfold too slowly for us to recognize as thought at all. The silence isn't empty, it's full of voices speaking in wavelengths we haven't learned to decode. The hunt for silicon-based life is shifting from theory to reality as space agencies gear up missions designed to probe the most alien corners of our solar system and beyond. Leading the charge is NASA Dragonfly, set to launch in 2027. This nuclear-powered drone will soar through Titan's thick orange haze, sampling methane lakes and organic dunes with instruments fine-tuned to spot anomalies. Imagine Dragonfly's drills sinking into hydrocarbon mud, searching not for DNA but for microscopic silica structures that self-organize too precisely to be random. Its mass spectrometer could detect bizarre molecular ratios, like silane gas bubbling from sludge where simple chemistry says none should exist, hinting at metabolic processes we've never imagined. Meanwhile, the European Space Agency's Jupiter Icy Moons Explorer, or JUICE, will arrive at Ganymede in 2034. While focused on ice-covered oceans, its sensors might catch whiffs of Eo's volcanic plumes, silicate-rich geysers that could carry molecular signatures of heat-loving silicon life. Future missions could go further. Robotic landers armored against Venus's corrosive clouds, drifting for months while analyzing sulfuric acid hazes for silica particle patterns that resemble microbial clouds on Earth. Or subsurface drills on Mars targeting ancient hot springs, where opal deposits might preserve fossilized silicon microbes in layered mineral archives. The real revolution, though, lies beyond our solar system. The next generation of space telescopes like NASA's Habitable Worlds Observatory, slated for the 2040s, will scan exoplanet atmospheres for unconventional biosignatures. Instead of just oxygen and methane, they'll hunt for exotic cocktails like silicon tetrafluoride, a gas that could indicate silicate metabolism. Machine learning will supercharge this search, training algorithms to flag atmospheric imbalances that defy natural chemistry. Picture an AI spotting rhythmic fluctuations in silica dust clouds around a scorching super-Earth, suggesting something is actively cycling minerals in ways geology can't explain. But finding silicon life requires tools as radical as the life forms themselves. Traditional microscopes won't cut it. We'll need atomic force scanners to read crystalline growth rings like biological records. Seismic monitors could listen for slow, rhythmic tremors in planetary crusts, potential evidence of vast silicate organisms communicating through vibrations. Some prototypes even test quantum sensors to detect subtle magnetic fields produced by flowing mineral blood. The challenge isn't just technological, it's philosophical. We're designing instruments to detect not just unknown life, but life that might not recognize itself as alive by our definitions. The stakes couldn't be higher. If these missions find even microbial silicon life, it would shatter the carbon monopoly on biology. Every desolate exoplanet dismissed as sterile might suddenly brim with possibility. Lava worlds, rogue planets, even the acid clouds of gas giants could harbor organisms thriving in conditions we once called impossible. Future textbooks might divide life into two epochal categories: before and after we discovered we weren't the universe's only recipe for existence. The search for silicon life isn't just about finding aliens, it's about rewriting the very definition of what it means to be alive. Lab experiments are pushing the boundaries of what we consider alive, blurring the line between biology and geology in ways that would make even the most imaginative sci-fi writers take notes. In a Tokyo lab, chemists have coaxed silica particles to self-assemble into intricate, lifelike structures that grow, replicate, and respond to their environment without a single carbon atom involved. These synthetic silica cells aren't alive by Earth standards, but they're flirting with the edge of possibility, showing how silicon could mimic life's basic functions under the right conditions. One startling experiment produced silica vesicles, hollow, bubble-like structures that selectively absorb certain molecules from their surroundings, eerily resembling primitive cellular membranes. Another created silica strands that elongate, split, and pass on structural memories to their offspring, a crude but compelling parallel to heredity. These lab creations reveal something profound. The building blocks of silicon life might already exist in nature, just waiting for the right catalyst. Take the famous chemical garden experiments, where metal salts in silicate solutions grow twisting, plant-like tubes. Structures so lifelike they've fooled microscopists into thinking they discovered new organisms. More advanced versions at MIT now use thermal gradients to make silica gels crawl toward heat sources, while NASA-funded research has shown certain silicate polymers can store and transfer energy in ways reminiscent of metabolic pathways. None of these systems are conscious or even truly alive, but they prove that silicon can exhibit behaviors we typically associate with biology: self-organization, adaptation, even a primitive form of memory. The real breakthrough came when researchers at the University of Glasgow engineered silica scaffolds that fold and unfold in response to pH changes, a synthetic version of the way proteins function in our cells. By doping these structures with light-sensitive molecules, they created silica protocells that move toward light, photosynthesizing in a crude sense. Another team in California designed silica particles that communicate chemically, synchronizing their growth patterns across distances like bacterial colonies. The kicker, some of these systems evolved in the lab, with random variations leading to improved functionality, silicon-based artificial selection in action. Yet the most tantalizing clues come from nature itself. Deep in Yellowstone's boiling acid springs, bacteria coat themselves in silica armor, hijacking the element's durability to survive where carbon alone would perish. In Australia's Shark Bay, microbial mats entomb themselves in stromatolites, layered rock formations built by living things. These aren't silicon life, but they're proof that biology can merge with geology in unexpected ways. Some scientists argue that certain cave crystals, which grow in branching patterns eerily similar to neural networks, might represent nature's own experiments in silicon complexity. These lab and field discoveries share a common thread. Silicon's limitations in water-based chemistry might vanish in environments we've barely explored. A synthetic silica cell that collapses in Earth's oceans could thrive in Titan's methane lakes or Venus's acid clouds. What looks like a failed experiment in our labs might be the prototype for life on a world with different rules. The ultimate lesson isn't that silicon will replace carbon, it's that life has more than one playbook, and we've only just begun to read the first chapter. Silicon might be the most famous alternative to carbon, but the universe's chemistry lab has far stranger ingredients waiting in the wings. Picture life forms built not on silicon, but on sulfur, organisms that breathe sulfuric acid instead of oxygen. Their cells fueled by reactions so toxic they'd melt human flesh on contact. On Earth, we've already found microbes thriving in volcanic vents where sulfur compounds spew like geysers. Now imagine scaling that up to a world where sulfur replaces carbon entirely, with chains of sulfur atoms forming backbone structures as complex as our proteins. These creatures wouldn't just survive in acidic hellscapes, they'd sculpt entire ecosystems around them, turning corrosive lakes into thriving habitats and toxic clouds into nutrient cycles. Then there's ammonia, a compound we associate with cleaning supplies, but in the frigid reaches of the outer solar system, it could be the solvent that breathes life into the impossible. At temperatures around -70 degrees Celsius, ammonia becomes liquid, capable of dissolving organic compounds in ways that mimic water's role in our biology. Ammonia-based life might resemble gelatinous blobs floating in the methane seas of Titan or drifting through the icy plumes of Enceladus. Their chemistry would be slower, their metabolisms adapted to cold so extreme it would freeze carbon-based molecules into brittle shards. Instead of DNA, they might store genetic information in nitrogen-rich polymers. Their cells plump with ammonia-resistant membranes that flex like rubber in the deep chill. But why stop there? Boron, an element often overlooked, could form intricate cage-like molecules perfect for storing energy or information. In high-pressure environments, boron nitride structures rival diamond in hardness, yet under the right conditions, they might assemble into something resembling biological machinery. Picture organisms with boron, bones, and metallic hydrogen veins, thriving in the crushing depths of gas giants where pressures turn gases into liquid metals. Even noble gases like argon, usually inert and aloof, could play a role in truly alien biochemistries. Under extreme conditions, these unreactive elements might form unstable compounds that fleeting life exploits before they decay. Think of organisms with lifespans measured in seconds, their entire existence a desperate race against atomic instability. The most radical possibility, life might not need solvents or complex molecules at all. Plasma-based organisms could dance in the upper atmospheres of stars, their bodies woven from magnetic fields and ionized particles. Or consider cryptobiotic life entities that exist in a near-permanent state of suspended animation, only awakening when cosmic conditions briefly align. These wouldn't be life forms as we understand them, but self-sustaining patterns of energy that persist, adapt, and even evolve. Each of these possibilities shatters the carbon monopoly. proving that life's true habit isn't a specific element, it's complexity itself. The universe doesn't care if biology is built from carbon, silicon, or something we haven't even imagined. It only asks that matter finds a way to organize, persist, and change. So while silicon offers one path to alien life, it's just the first page in a chemistry textbook with chapters we've yet to read. Silicon-based life isn't just a scientific hypothesis, it's a doorway to a universe far stranger than we've dared to imagine. Every assumption we've ever made about biology, from the necessity of water to the primacy of DNA, gets turned on its head when you consider creatures built from molten rock or crystalline lattices. The possibilities we've explored: lava-dwelling organisms, methane-breathing microbes, civilizations operating on geological timescales, aren't mere fantasy. They're logical extensions of chemistry playing by rules we're only beginning to decode. These ideas challenge more than our understanding of alien life. They force us to confront the arrogance of defining life solely through Earth's narrow lens. Think about the implications. If life can flourish in the acid clouds of Venus or the methane lakes of Titan, then the universe's habitable real estate expands exponentially. Planets we once dismissed as hellish or frozen might be teeming with biology we simply lack the vision to recognize. Even Earth could harbor undiscovered silicon-based extremophiles in its deepest volcanic vents or most barren deserts, organisms so alien they've been hiding in plain sight. The search for life becomes not just a quest to find others, but a mirror held up to our own cognitive limitations. How many marvels have we overlooked because they didn't fit our carbon-based expectations? This isn't merely academic. Discovering silicon life would rewrite textbooks from biology to philosophy. It would prove that life isn't a fluke of Earth-specific conditions, but a fundamental property of matter under diverse circumstances. The ethical ramifications alone are staggering. How do we interact with intelligences that perceive time in millennia or communicate through seismic vibrations? Our entire legal and moral frameworks assume biological kinship that might not exist with silicon beings. They could be the universe's elders, watching our fleeting civilizations rise and fall like seasonal blooms, their patience making our most long-term thinkers seem impulsive by comparison. So where does this leave us? Not with tidy answers, but with better questions. Instead of asking, "Are we alone?" we should wonder, what counts as being here at all? The cosmos owes us no promise that all life will resemble Earth's template. Silicon organisms might not just be different, they could be fundamentally unrecognizable by our current standards, their very existence forcing science to expand its definitions. That's the true gift of this thought experiment. It liberates us from planetary parochialism. The universe likely teems with life, but not necessarily as we know it. So let's end with a challenge not just to scientists, but to every curious mind watching. Look at the night sky and ask, could reality be weirder than our wildest dreams? The answer might already be out there, written not in flesh and blood, but in stone and fire, waiting for us to learn how